Hi, this is Mark Holdsworth with PastoreHouldsworth and Company, and this video is a demonstration of our Neural Navigator product. It's an artificial neural navigator engine, neural network engine, and it can really give you a predictive edge in a variety of problems in trading energy or whatever you're trading. Um, so we have a problem here. We'd like to predict something. In a regression framework, we'd think about having some X data and some Y data. So let's describe that data quickly. Over on the X data, we've got month, year, intercontinental airport, heating degree days, and cooling degree days. And we'd like to use that data to predict this data. So what I have over here is just the ratio of the upreg divided by the 5 by 16, the downreg divided by the 5 by 16, and the other two key ancillaries in ERCOT. So again, these are averages over the month. And we'd like to be able to take this data and predict this data. Undoubtedly, if you were working on this problem yourself, you'd have a lot more information on the X data. But let's start with this and see how we do. So with that in mind, basically, using the Neural Navigator, you would take the output data and drop it into this Training Output tab. And you would take the X data, or the input data, and just drop it into the Training Input tab. So it would look like that. Then we'd have basically a setup here. So we're going to start by selecting a couple of parameters here. The number of hidden neurons basically derives how much nonlinearity is permitted inside the solution, and that's a user selection, and you can try a bunch of different ones. An epoch, a single epoch, is just a single pass through all the data. There's a gradient descent routine that goes on behind the scenes, and it determines all of these weights from the hidden to the output layer and from the input to the hidden layer. So for smaller problems, this tool can handle problems with 50 input variables and 50 output variables and 15,000 rows of data, if you like. But we can just set that up like that and punch the button. And for smaller problems, we have this graph. It chews up a bit of memory for really large problems. But you get the idea what's going on here. What's represented is the square root of the squared vector output prediction error. And it starts off sort of clumsy, not very well trained on the far left over here, and then as it goes through time, through the gradient descent routine, it gets smarter and smarter, and then it finally quits. It says, okay, I'm smart, I've learned enough here. And if you had a problem that required more epochs, you put 25,000 in there, and then probably turn the chart off. And this will pass through the data 25,000 times. And the weights come up there pretty quick. Okay, so how well does this thing predict inside the sample? That's one of the big frustrations using linear regression routines, is that frequently not only can you not forecast very well with them, but you can't even predict stuff that's inside the sample set if it's a highly nonlinear problem. So let's have a look and see how well this one does. So let's say we had, let's just pick a handful of these. Let's pick, copy those. And we're going to put those on the prediction input page. And that will generate predictions using all the weights that we've stored on that setup page. And we've got some answer over here on the prediction page. So how well did it do? Well, to see how well it did, we'd have to go find 26 through 30. The output associated with those inputs is here. put them next here and we can see how close it was. So 27 versus 27 pretty much, 23 versus 21, and 27.1 versus 26, pretty close. Go down and look at the August of 11, which was a blowout month. So 48 versus 48, and then 5 versus 5 for the down regs. So pretty close. Now let's ask the question, okay, well, how well might I have done with a linear regression? Let's go back over here. So if you were going to try to do this using the linear regression in Excel anyway, you go to the Data tab and you go to Data Analysis and you pick Regression, and it's already been pre-selected here. We've got the input Y range covering there, and then the X range over here. We have labels, and let's click OK. And of course you see the first problem, right? At least in Excel and many regression packages, the most you can do is one output range. So you're going to do 4 different regressions so that your coefficients are not being determined coherently whenever you use a linear regression, most of these linear regression routines. Let's cancel out of this and cancel out of it. So what would you do next? Next thing you do is just, okay, well, let's do one at a time. So let's say I just did the up reg divided by the 5 by 16 and did that regression. And I'm going to cut to the chase because I've already done it here. So let's go, and here's the regression output here at these coefficients, and here's the comparison, I guess, over here. So basically, here's the same data we looked at a minute ago. So there's the May through September of 2011. Here is, for that data, what the linear regression would have produced for an estimate. So 31 cents, or 31% rather. And the neural predicted 27, and the actual data was 27.3. For the month of August, we had the linear regression predict 26, and the neural predicted 48.1, and the actual data again was 48. So you get the idea that you can certainly predict much closer inside your sample set, and you're not going to be able to predict well outside your sample set if you can't predict well inside your sample set. So the neural navigator, the artificial neural network that's sitting behind this thing, can predict very, very well over a lot of using nonlinear techniques over a lot of different kinds of problems. You can handle 15,000 rows of data again, and 50 input variables and 50 simultaneous output variables. Give us a call, either Rich or myself, Mark Holdsworth again, and we'll be happy to do a personal demonstration in the office, and I want to thank you for your time.